Welcome to this lesson on kinetics. Well, what is kinetics, you might ask? Kinetics has to do with motion, and specifically in chemistry, kinetics is the study of reaction rates. How fast a reaction goes, and what are the factors that can affect reaction rate, and that's going to be the topic of this lesson. So the study of reaction rates, speed. Right, so the faster it goes, the less time it takes, and the slower the reaction goes, the more time it takes. There's something called the reaction mechanism, which is effectively the steps in a chemical reaction. When you see a chemical equation, it makes it look like everything just happens so nice and neatly. The two reactants might easily turn into the one product, but oftentimes from starting with reactants and heading towards products, there are multiple steps, and this is what we call the mechanism, like the actual route that the chemicals take in order to become the products. So this series of steps that is required to complete the reaction is known as the reaction mechanism. Before any chemical reaction can take place, there's something called collision theory. Reactants must collide with each other in order to react, but they must collide effectively. You can't just have a casual bump of two chemicals and have them react. So there's a couple things that have to happen. The particles must have enough energy. Right? And so what we're talking about is they must be moving at a certain speed in order for the collision to have enough energy associated with it to trigger the reaction. This is what is known as activation energy. The other thing that must be true is that the particles must be in the correct orientation. The particles must bump into each other in the right manner, or else the atoms might not be lined up properly in order for rearrangement to take place. So assuming that there's an effective collision, what happens next is any bonds that were present in the reactants will break. And when you break bonds, this is a process that requires energy. Energy needs to be absorbed in order to break a bond. Once you get any old bonds broken, atoms will then rearrange into something called an activated complex, and we'll be talking about that a little bit later on in this unit. So this is not fully formed products yet. It's sort of an intermediate product that is said to be the activated complex, and it's at a pretty high energy. Again, we'll come back to that later in the unit. Once the atoms rearrange, then new bonds, if any, will form. And since it requires energy to be absorbed to break a bond, when you form a bond, this is a process that releases energy. So let's take a look at a possible mechanism. For this reaction, we've got two reactants, one product. So let's just take a look at our reactants. Are there any substances here that have chemical bonds already in them? Well, the carbon is an element, so there's no bonds there. But this oxygen molecule does have a bond in it, a double bond between those two oxygens. So we are going to have to break that first. So let's just focus on that O2. And it has to turn into O plus O. Okay, so once we have this O2 broken into O and O, then the C and the O can start to interact with each other. So let's take that carbon and let it react with one of the oxygens. And we would get something here, a CO. This is not the final product. It is the intermediate activated complex. We're not done with this reaction because this oxygen was accounted for, but this one wasn't. So our third step might be for this CO to react with this O to get CO2. Okay? And so we know that all of this might happen But what we want to recognize is that this is what we call the net reaction. This is the overall reaction that happens. So let's just simplify. If we needed to simplify this, any chemical formula that shows up on the left side of the arrow and the right side of the arrow, even if it's in another reaction step, we can cancel it. So I see here this CO and this CO on the right, on the left, those cancel out because when it gets produced, it just gets consumed over here. I see two oxygens, one on the right, one on the left. This one's produced, but it didn't get consumed right away. This one's produced, this one's consumed. So what we see here is things that don't cancel out. C plus O2 turns into CO2. So that's where we get the idea that this is the final reaction and all those intermediate things just kind of disappear. Now, I'm not going to ask you to do this on a test, but it's just sort of an interesting thing to consider. For this reaction, H2 plus I2 turning into 2HI, let's take a look at our reactants. We have bonds that need to be broken. So the H2 is going to have to break into H plus H. The I2 is going to have to break into I plus I. And now that we have all the bonds broken, we can start to rearrange, right? So we can have this hydrogen plus this iodine turning into HI. And then we can have this hydrogen and this iodine turning into a second HI. So if we, again, simplify all of this, right, I see an H produced, an H consumed. H produced, H consumed. Iodine produced, iodine consumed. Iodine produced, iodine consumed. So what I am left with is H2 plus I2 turning into 2HI. Okay? And these are possible mechanisms that can happen. Again, I'm not going to ask you to repeat this on a test. It's just to show you that there are reaction mechanisms, and we can potentially manipulate these reaction mechanisms if we want to manipulate the speed of the reaction. So let's take a look and see what's involved in that, right? So that mechanism, that series of steps is going to determine the base rate, or how fast the overall reaction takes place. And if one of those steps is the slowest step, we would refer to that one step as the rate determining or rate limiting step, because if you had 5 steps in a reaction and step number 3 takes I don't know, several minutes as opposed to the other steps taking only seconds, then that third step is going to, by and large, determine the rate of the overall reaction. All right, so let's talk about defining what reaction rate is, right? So reaction rate is a speed. We can think of it as the reactants consumed over a given period of time. So the reactant rate is the rate at which reactants are converted into products. To get a faster reaction, you need more collisions. To get a slower reaction, you need fewer collisions. So let's talk about this. A faster reaction is going to take less time and therefore a faster rate. A slower reaction is going to take more time and therefore will happen at a slower rate. All right, let's talk about factors that can affect this reaction rate by talking about the mechanism, those series of steps. Think of this as if you had your GPS taking you to location B from location A. And if you were to somehow, you're driving along and all of a sudden there's a detour and you have to take a different road to get to your destination, and that different road makes your trip be longer, right? That's like a detour, typically adds more steps to your reaction. This in chemistry is known as an inhibitor. And this is going to make the reaction go slower without getting used up. And that's typically by adding steps to a mechanism. Now, what if your GPS suddenly woke up and realized that there was a shorter way to get to your destination by cutting out one road altogether, like a shortcut? So removing steps from a reaction is, in chemistry, happens when you add a catalyst, and it makes the reaction go faster without getting used up by removing steps from a mechanism. All right, so those are factors that affect reaction rate by manipulating the steps. Inhibitor will slow it down, a catalyst will speed it up. Let's talk about factors that affect reaction rate by manipulating the number of collisions, right? Because you got to have collisions for a reaction to happen. So let's talk about that. There are three factors we're going to look at: the temperature of the reaction, the concentration of the reaction, and the pressure. Pressure will affect gases only. All right, so temperature. If you increase the temperature, what are you doing? You're increasing the temperature, you are increasing the kinetic energy of the particles. So that means you are increasing the speed. And increasing the speed, you are going to be increasing the number of collisions that will happen, and you will also be increasing the force of the collisions, right? So that's a possibility that not only will you have more collisions, but you'll have you will have an increased force of each one of those collisions, making sure that more of those collisions are effective collisions, right? So when you increase the number of collisions, any way that you can increase the number of collisions, you are increasing the reaction rate. Concentration. Concentration is when, if we consider molarity, right? Molarity is equal to the moles, the number of particles per liter of solution. So if you increase the molarity, you are basically increasing the number of reactant particles. Or in a gas, you can decrease the volume of the container. If you decrease the volume of the container, then you are basically shoving those particles closer together, right? So that's, you can do that there. But typically, we're talking about an aqueous solution, so we would need to either add more particles, or we could evaporate some of the solvent out, making it more concentrated, right? So basically, either one of these situations, this is for an aqueous situation, you would decrease the volume if it was a gas situation. But the idea is that you're packing the particles closer together when you increase the concentration. And so that is going to increase the number of collisions. And the more collisions, you will have a faster or increased reaction rate. All right, pressure will affect gases only because gases are compressible, right? There's so much space in between them. If you increase the pressure, right, what you're doing is you're actually decreasing the volume and making those particles closer together. So that's effectively an increase in pressure on a gas will increase its concentration. And then we're back to this concept, right? So increase in concentration will increase the number of collisions and thus make the reaction rate go faster. All right, there's a fourth factor that is called surface area, and this is going to affect solids only. This diagram is not super easy to see, but here we have a cube, a single cube. Here we have the same size cube, but it's broken down into smaller cubes. So now all of a sudden, everywhere we've cut here, we have increased what we say the increased surface area. And the more surface area you have, that means there's more particles that are now available for reacting with whatever you are putting this solid solute with, right? So like whatever you're reacting with can sneak down into these cut areas, and there's more exposure to the particles, right? So when you increase the surface area, you are making each particle smaller. When you make each particle smaller, you are increasing the surface area and giving an opportunity for an increased number of collisions and thus a faster reaction rate. All right, so nature of reactants. Nature of reactants has to do with what the reactants are made of, basically. Every chemical is going to have its own base rate of reaction, which is dependent on sometimes it's just referred to as the nature of the reactants, but really what they're saying is what kind of bonding does it have? Because what kind of bonding it has is going to dictate what properties it has. If we look at sodium carbonate, Na2CO3, it's an aqueous solution. This is an ionic compound, and if we react it with an aqueous solution of cobalt chloride, also an ionic substance, right? This is a double replacement reaction, which you have seen in class, and there is a precipitate that forms, right? And this is instantaneous. And the reason why it's instantaneous is because when we dissolve this ionic substance in water, water acted as a catalyst and these ionic bonds were broken. So remember we said in a reaction, bonds have to break before atoms can rearrange. So when you are dissolving this in water, you are saving that first step, right? You are taking those ionic bonds and they are previously broken when they dissolved in water. And in this case, we said water acts as a catalyst. So as soon as you take those aqueous solutions and mix them together, the precipitate is going to form instantaneously, right? So because they're ionic and because they are dissolved in water, they are, it is an instant reaction, okay? So sucrose and concentrated sulfuric acid, these two substances are covalent. And when we pour concentrated sulfuric acid onto sucrose, a most remarkable reaction takes place, but it is very, very slow. I will post the videos of both of these reactions in these notes if you're watching this as an absent student, so that you can see the differences in how quick these reactions take place. This one is very quick, this one is really quite slow. So this is a very slow reaction because the covalent bonds need to break first before rearranging, and it takes a lot of energy to break a covalent bond, so it's slower. So generally speaking, ionic reaction rates are fast, and covalent reactions are very slow. All right, so in this lesson, we have looked at what kinetics are. It's a study of reaction rates. We have looked at what a mechanism is, basically understanding that a chemical reaction has a series of steps that need to happen in order for the reaction to take place. We've looked at factors that affect reaction rates, adding an inhibitor or a catalyst. Those factors are affecting the number of steps that a reaction takes, thereby affecting how fast the reaction takes place. But we can also manipulate the number of collisions that take place by manipulating the temperature, the concentration, the pressure if it's a gas, the surface area if it's a solid. And then we looked at nature of reactants. Just the inherent bonding that is in a chemical reaction will also play a big part in determining whether a reaction is fast or slow. All right, there it is. There's our lesson on kinetics. We'll see you back in the classroom.